So today we're going to talk about how to find the area of a regular polygon. Now, regular polygons are the nice kind of shape. All their sides are congruent and all their angles are congruent. So when we solve these, I'm going to start by describing it as a polygon that's been inscribed inside a circle, which just means that the circle goes through each point of this polygon. So what I have here are a series of steps we're going to follow. The first step is to draw a triangle by connecting the radii. Radii is like radius, and I'm using that language because if you take a look at these two pictures down below, the center of a polygon is the same as the center of its circle. So any line connecting that center to the vertex is the same thing as connecting the center to that point on the circle. When you draw these radii, you're going to get a bunch of triangles. We then want to go ahead and find the central angle. Now the central angle is just the angle between the two radii. Now you're going to draw a line that bisects the central angle and the triangle side. And when you're doing this with a pencil, you're just going to sketch the line and then find those missing parts. So we're going to take that central angle, going to cut it in half. So if it was 40, it's now 20 degrees. Now notice that when we're doing this, we're going to form a right angle. Basically, what we've just done is found the altitude of an isosceles triangle. It so happens that means that the central angle will be bisected as well as the triangle side because it is both a perpendicular bisector and an altitude. These are special properties of isosceles triangles. Now, that segment that connects the triangle side to the center has a special name. It's called the apothem. So in this first picture, that red line, that segment from A to C is the apothem. And in the second, that segment PQ is the apothem. Just a special name. From there, you can either use special triangles, so 30, 60, 90, or 45, 45, 90 if you've been given those angles, or regular trigonometry, so Katoa from chapter 9, to solve for the height and base of the triangle. So if we're trying to find the area of this polygon, we're going to do it by breaking it into triangles, finding the area of a single triangle, and then multiplying by the number of those congruent triangles that we have in this polygon. And that's what I'm saying below. So area of a triangle is 1/2 base times height. And remember that base and height are perpendicular. They're where that right angle happens. You're going to multiply that triangle area by the number of triangles. And do know that the number of triangles is the same as the number of sides in your polygon. If you look at this right figure here, angle MPN, that's an example of a central angle because between the two radii. Okay, so moving on, notice what we've said here. S is going to be that side length, so all the way across that side length of the triangle. A is the apothem, that's the height of the triangle. That's something important to note. Apothem and height are the same thing. N is the number of triangles. So notice that 1/2 SA, that's basically 1/2 base times height. This stuff in parentheses is the area of the triangle. Times the number of triangles gives me the full area of this polygon. Now, see what they did next. They regrouped the parentheses, and they also changed the order. The regrouping of parentheses, that's called associative property. The changing the order when everything's being multiplied, that's called the commutative property. Now, notice here, if they group N and S together, what is that saying? I have the side length times the number of sides. That's another name for perimeter. So what they've shown is that we have this other formula, 1/2 AP. You can use that too. And it's all boiled down nicely right here. So the two nice ways of finding area of a regular polygon, you can either think of it as 1/2 times A times N times S, or 1/2 ASN, like 1/2 base times height times number of triangles, or break it down to be 1/2 apothem times perimeter. So again, lowercase a is apothem, that height. S is the side length of a triangle. N is the number of triangles, and P is the full perimeter. Both of these formulas will do the same trick. Alrighty, so here's an example question. Using the center we've just decomposed a regular hexagon into 6 triangles. So here's my center of both the circle and of my polygon. And the question is, what kind of triangles are these? Well, before I do that, I want to make sure I've labeled everything I know about this. So I know it's a regular hexagon. So I'm going to start by saying that all these side lengths are the same. Okay, so I know all of that is the same. Okay, so I have the outsides marked. Let's take a look at these angles here. So remember, a full circle adds up to 360. Whatever these angles are, they have to be the same. I have 1, 2, 3, 4, 5, 6 angles. So I'm going to do 360 divided by 6. Each of those central angles must then equal 60 degrees. I'm going to go ahead and label that. 60 degrees, 60 degrees, 60, 60, 60, and 60. So they're all the same. They're all 60 degrees. Okay. Think about this big polygon. Now remember, back in chapter 7, we talked about how to find the sum of the angles inside a polygon. Remember what that formula was 180 times n minus 2. If I want to find the measure of just one angle, divide this value by n. And again, this stuff here comes from chapter 7, where n is the number of sides. In a hexagon, that's 6. So 180 times 6 minus 2 over 6. 6 minus 2 is 4, but I also know that 6 goes into 180. 30 times 6 goes into 6 once. So I have 4 times 30, which is 120 degrees. Now let me show what this part is talking about. 120 degrees is like saying all of this stuff put together. Everything there is 120 degrees. So this is all of that. But do also note that this radius is going to cut that angle in half. So basically 120 divided by 2, that's our 60. So each of these up here is also 60. Remember that each of these big angles is 120. Everything here has been cut in half. And what I'm doing right now, this will work for all regular polygons. Whatever the measure of one angle is, just divide it by 2. That's 60, that is 60, and that is 60. And yes, these all are in degrees. Okay. Alrighty. So now notice what you have. 60, 60, 60. That's an equilateral triangle. Now, if that's an equilateral triangle, then that means that all angles are the same, which we have, and all sides are the same. Which means the radii is the exact same size as that outside length. So when they ask you, what kind of triangles do we have? What we just showed is that what we have here are equilateral triangles. So they're equilateral, lateral, and equiangular, because all angles are the same as well. And that happens at the same time, just 2 vocabulary words we get to use. So equilateral and equiangular answers their question. We have up here is the work we did to fill in this picture. Now it says draw one triangle here and label only the vertex angle. We want to find the area of the triangle given that the radius of the circle is 2 centimeters. Okay, let me go ahead and draw myself a triangle here. Okay, and they've told us that the radius is 2. So remember, if this triangle is coming from right here, like this one is that one, radius is 2 up there. And to do this part, I put a 2 down here also. So this full thing here is 2. My next step is to draw the apothem. So the apothem comes down like this. Now notice that that vertex angle they were talking about, that big thing here is the 60 degrees. This thing here is 60. Remember, the apothem cuts that 60 in half. So this up here is 30 degrees. This up here is 30 degrees. And remember, in the bottom, These were 60 degrees. Now, an equilateral triangle is a special type of isosceles. Remember, isosceles means there's two congruent sides. Equilateral just means there's a third congruent side. So in those types of triangles, that apothem is also an altitude. So it meets at a right angle. Take a look at what we have here. 30, 60, 90 triangles. Now, if these two triangles, notice the left triangle and the right triangle, if they are congruent, that means this 2 has been cut in half. This is a 1, and that is a 1. What we need to find next is the height. So I'm going to go ahead and separate this triangle one more time, just to make sure you're really clear at what I'm looking at. So right angle, 60 degrees, 30 degrees, 2, and 1. Now you can use trig to solve this, but why bother? All we need to do is find the height. Now notice that the height is opposite the 60 degrees. To find that value from our 30, 60, 90 triangles, what we have to do is that short side times root 3. So the thing we're missing is 1 times the square root of 3. Just root 3. You can fill it in right here. Just root 3. So to find the area of the triangle, they're not talking about the small one, they're talking about the big one. Okay, so area of that big triangle is 1/2 times the base of 2. Come through and use that black for 2. Times the height. And the height is the root 3 that we just found. Well, half of 2 is just 1. So my area is square root of 3, and units are centimeters squared. If you want to have a decimal out, I can show that as well. Square root of 3 is 1.73. So this is approximately 1.73 centimeters squared. I'm going to go ahead and box that off. Now it says, what is the area of the hexagon? Well, we just found the area of one triangle. So we can go ahead and take that area, multiply by the number of triangles. 1, 2, 3, 4, 5, 6. So the area of the hexagon this time equals 6 root 3. And again, these units are centimeters squared. Centimeters squared. And if you want to get out a decimal, 6 radical 3, 10.39. So this is approximately 10.39 centimeters squared. Then it says, what is the perimeter? Well, actually, this is the one thing we could have answered first if we'd wanted. Remember that this length is 2? Well, coming back to your picture, when they're telling you that part is 2, they're referring to this side length right there being 2. This is 2, 2, 2, 2, 2, and 2. So perimeter is 6 sides times a length of 2, 12 centimeters. Now I do want to note, okay, this is 12 centimeters. One of the methods of finding the area of a hexagon was using 1/2 times A times P. So I'm going to actually write that down as a note down below here. So this is the work I've shown so far. I do also want to make this note over here. If using 1/2 AP, so I'd have 1/2 times my apothem, which was radical 3, then times my perimeter, which was 12. 1/2 of 12 is 6. 6 root 3 is another way of finding that area, centimeters squared. So this here is method 1, area of triangle times number of triangles. Over here, I'm using the other method, 1/2 apothem times perimeter. Same answer in the end. Okay, let's take a look at another example. This one is an octagon. And they asked me to first figure out how many triangles are there and what kind are they. So let's go ahead and draw in those radii. Just making a sketch. If I wanted it to be exact, I would totally grab a ruler. But I just want you to see what this thing looks like. Okay. So this time I have 1, 2, 3, 4, 5, 6, 7, 8 triangles that have to be the same. Again, the central angle is always the same. So I am doing 360 divided by 8. And that is 45 degrees. So what that means is that each of these central angles is 45 degrees. All 45 degrees. Okay. Now we also know that all of the radii are always the same. So let's put those down. These are all the same like this. Okay. Let's go ahead and find these angles here. So remember what we can do is 180 times n minus 2 over n. This time n is 8 because I have 8 sides. So 180 times 8 minus 2 over 8. Okay. So 8 minus 2 is 6. And I have 180 and 8. There's a variety of ways you can break it down. I'm just going to go ahead and rewrite it as simplified. 180 times 6 over 8. Okay, so what I'm going to do is I'm going to divide 180 by 4 because I know it's going to go into it. So 180 divided by 4 is 45. So this is now 45. This is now 2. And I can come through and say, all right, I have 6 and 2. Divide those by 2. That's a 1. That's a 3. Multiply straight across 45 times 3. So 45 times 3, and that's 135 degrees. Okay, now that's the measure of one angle. So again, what we just found, let me switch colors here. We just found that one angle, like this entirety of this angle here, is 135 degrees. Let's go ahead and cut that in half. So 135 divided by 2 is 67.5 degrees. Okay, so all of these are 67.5 degrees. And again, their actual question was, what kind of triangles are there? So we have 8 triangles, and their type is just isosceles. They're not equilateral. So these are isosceles. And how do we know? Well, base angles are congruent at 67.5 degrees, and sides are congruent. And that's because they are radii. So notice that when we are doing this, let me kind of separate this here, and I took up more space than I thought. When we're doing this, notice that these triangles are either equilateral or they're just isosceles. You would never have scalene. Either these two sides are the same only, or all 3 are the same. There are no other choices. So again, what I just said here, they're isosceles, base angles are congruent at 67.5 degrees, and sides are congruent because they are radii, and all radii have to be the same in the same circle. So we're going to go ahead now and redraw that triangle. Slide this up here. Okay. And so we know that this top thing here is 45. I'm going to go ahead and draw in that apothem. Remember, it's going to form a right angle. Remember that we know that this bottom part here is 67.5 degrees. That's this arc right here. For this top part, we're doing 45 divided by 2, and that's 22.5. So this angle here is 22.5 degrees. So again, what I just did is I said 45, that central angle, divided by 2 is 22.5 degrees, and that's what happened here. Draw the little arrow. 22.5. Let me go ahead and zoom in a bit. Okay, So they told us that the radius of the circle is still 2 centimeters. So that's our 2. And this will be 2 here also. Okay, so this time we have to find the height and we have to find this base. Okay, so I'm going to say we should do this using trig. We can't use special triangles this time. So I'm going to label it with respect to this angle right here. Okay, so basically I'm going to say stand at this angle. It's your choice what angle you pick. Stand at this angle. Over here, I have opposite. Right here, I have adjacent. And here, I have hypotenuse. Let's say I'm trying to find the opposite. If I'm standing here, I'm going to do opposite over hypotenuse. That's the SO in SOHCAHTOA. So I'm going to do the sine of 67.5 degrees equals opposite over 2. And you can use opposite as X or O or whatever you want. The reason I don't recommend using O when you write it in is because O looks like 0. So to get that by itself, multiply the 2 to the other side. So 2 times the sine of 67.5 degrees. Type it into a calculator. So 2 times sine of 67.5. And I noticed that my calculator is in radians right now. I'm going to switch it to degrees. So on my calculator, I go to mode, I switch it back to degrees. So 1.85, that's going to roughly be that opposite. So I'm going to say, let's make this approximate 1.85. You can note down below here. So opposite, that's the same thing as apothem. And it was roughly 1.85. Okay, now we need to find the adjacent. Well, adjacent hypotenuse, that's cosine. So cosine of 67.5 degrees equals adjacent over 2, multiply 2 to the other side. So 2 times cosine of 67.5 degrees. I'm going to go ahead and type that one into the calculator as well. So instead of sine, just using cosine, 0.77. So 0.77. So again, what we just found is the adjacent, which is the same thing as half of that. I'm just going to leave it as adjacent right now and title it as 0.77. And that entire side, so side equals 2 times the adjacent. 0.77 times 2 is 1.54. So again, everything here is 1.54. Just one of these is 0.77. Okay, now our job right now is to find the area of one triangle. Let's do that off to the side here. So area equals 1/2. The base is 1.54 times the height, which is the apothem, 1.85. 1.85. Okay, let me make that a better 5. Alrighty, go ahead and type it in. So I have 1/2 times 1.54 times 1.85. So the area of a single triangle is approximately 1.42, and the units are centimeters squared. So remember, the apothem, which is opposite in this case, is the same thing as height. So the area of the octagon, so area of octagon, you can label it oct if you want. It's optional. This is going to be 8 of those triangles. So 8 times 1.42. So 8 times 1.42, 11.36. 11.36 1.36 centimeters squared. And finally, that perimeter. So perimeter is the number of sides times that full length. 8 times 1.54. So 8 times 1.54. 12.32. So this perimeter is 12.32 centimeters. And again, if you'd wish to use that other method, so if using 1/2 pothum times perimeter, you'd have 1/2 your apothum. So again, that's 1.85 times the perimeter of 12.32. So if you did that, let's come back here. 1/2 times 1.85 times 12.32, 11.396. Now do notice this number is slightly different than the other one, and I want to show you why. So 11.396. Again, what I had before was 11.36. Again, this is centimeters squared. Now notice why this is. I rounded at a different place, and this is important. So come back up to here. Notice what happened, but I had to round to get those values when I got down that 1.42. So let me show you again what happened up here. 1.54 times 1.85 times 0.5. I truly got out 1.4245, not just 1.42. When I used 1.42, I got out 11.36. Let's see what happens if I do 8 times that value. So times 8, now I get the 11.396. So back over to here, I'm going to make a note. This one had extra rounding. Extra rounding. Because this one here is better to use 1.4245. If I do area of octagon using that value, 8 times 1.4245, now I get the 11.396 centimeters squared. And that's why it's important to pay attention to what values you have. So to be the most exact, you don't want to round until the very end, which means if I wanted to be as exact as possible, I would have left the stuff in terms of cosine until the very end. In an assignment, I'll probably either give you multiple values or I'll specify what method to use and when to round to.